Let's make it start. Hi, everyone. Welcome. Thank you very much for coming to the Toronto Java Workshop. Very, very happy to have Maurice Greenberg today from the University of Toronto. He's going to be talking about the past, present, and future of Scrabble engines. He's a fifth-year PhD student. He's advised by Kieran Campbell and Radu Craiu. Uh, Academically, his interests lie at the intersection of Bayesian methods and high-dimensional healthcare data. I knew him as a baseball analyst. I knew that side of his life, and so when he mentioned he was actually 10th in the 2017 North American Championships of Scrabble, I was shocked. And when he was mentioned that he was working on Scrabble AI, I was shocked and impressed. So I immediately knew that we had to get him in. So thank you very much, Morris, for agreeing to give us a talk.
For sure, and thanks, Rohan, for this opportunity. Um, so yeah, as Rohan kind of mentioned, I'm aside from doing my PhD in stats, where I focus a lot on sort of Markov chain Monte Carlo methods and high dimensional data, specifically geared towards healthcare. On top of that, I really enjoy Scrabble. I have done pretty well in some tournaments. And I would say I right now kind of contribute conceptually is the nice way to put it, in kind of the two current cutting edge Scrabble AIs being developed by like people in the Scrabble community who are very skilled in a computer science sense and kind of building things, but don't have as much sort of statistical inference or machine learning knowledge necessarily. What that really entails is kind of spamming their Discord often and with crazy ideas, and they indulge me a bit. But today I'll kind of talk about what the kind of challenges behind analyzing Scrabble as a game compared to other games that places like Google DeepMind have successfully built engines for. And I'll go through kind of the past, present, and where I hope the future will be with how engines have been created in Scrabble. So, for those not actually show of hands, is are people pretty familiar with Scrabble here, or is anyone not familiar? Okay, cool, cool, cool. So I mostly see head nods, so I'll go through this pretty quickly. But basically, quick rule of Scrabble is you want to maximize your cumulative score across all turns, and the winner has the highest total. So over the kitchen table, there might be up to four players playing. In tournaments and in computer analysis, it's normally a one-on-one game. And so, how do you actually score points? Well, in each turn, a player creates one word by adding tiles in a straight line contiguous with existing tiles on the board. So, a board will like kind of have a lot of right angle looking shapes
Morris,
where all these
Morris,
what?
sorry to interrupt you. Are you sharing a screen at the moment,
Oh,
or are you
you know what?
talking?
I am sharing a screen, and I forgot, or I did not try sharing. I'm going through slides, but I forgot to share. So, sorry.
Okay,
I
sorry for
will.
interrupting you.
Yeah, yeah, that's totally fine. I completely forgot. Uh, cool. So just and can people still see?
Perfect. Yeah. So we've got a young photo of you.
Yeah. This was me showing my Scrabble credentials. But in terms of, but I think on this slide where it's just sort of describing, yeah, how Scrabble's played, right? Maximize cumulative score across turns. Winner gets the most. It has the highest total. On a turn, basically, how can you create these points? You create some sort of word by adding tiles in a straight line contiguous with existing tiles on the board. So a board might look like this, where we have all these sort of right angles and words. Some of these look obscure, but they're all valid in the Scrabble dictionary. And how the point value of a specific turn is just the sum of letters. So every unique tile has a specific point value. Vowels are worth 1 point. The Q and Z or Z uh, are worth 10 points. And then the other way you can score points is if you use all seven of your tiles, you get a 50-point bonus on top of whatever those kind of score is based on the point values of tiles and board dependent multipliers. And finally, the game ends when the tile bag is empty and a player finishes their remaining tiles. Or if that's not possible, all players will pass a few times, and that just terminates the game. And then unplayed tiles will just be subtracted from players' scores. So pretty simple rule set. But let's just kind of go through an example just to make sure we understand how we can actually make a move. So let's suppose we're in this position where at the beginning of the game, our opponent started the game with cat. How can we actually play a word that kind of creates a straight line of tiles? One way is we could play through an existing tile, so we could take inspiration from our opponent's cat and play cat ourselves. Another way is we could play parallelly, so long as all the words it creates in the other direction are also valid words. So in this case, may forms ma, shorthand for mother, and at, common word. So that would be another way we can make a valid play. Third way is if we hook a word where the hooked version of the word is also valid. So scat is also a valid word, so we could play clays and scat. Does anyone see a fourth way where we could, of how we can make a word? Let's see in the chat. Yeah, so through shout out to my brother. Through existing word on the board. So in this case, actually the highest scoring play available is cataclysm. So right, and not only does that hit a triple word score here, but it uses all of our tiles. So this actually would score over 100 points and is a much higher score than any possible play here. So those are the four ways you can actually make a valid play. But you can imagine as we add more words to the board, the number of possible moves just explodes. So I'm just going to go through three quick examples to sort of motivate where an engine could Scrabble. So the first, going from like least complex to analyze from an engine perspective to most complex. So this first position came from this past summer at a tournament called the Word Cup, where this is a game from the best player in the world, Nigel Richards. And this position, we have perfect information. Scrabble starts off with 100 tiles, but as you play words on the board, you replenish your seven letters, and eventually, when there are no more tiles left in the bag, you know exactly what your opponent has. So in this position, Nigel has these seven tiles, and his opponent just has a V. And so Nigel played the optimal endgame. He solved it within minutes. It's quite a beautiful solution, so I'll show it. And in endgames, and the computer is also able to solve it very quickly, probably under a minute. So how does he go about this? Well, the first thing to notice is the V, the one tile his opponent has left, has only one place on the board, specifically in front of OW to make Val. If you look closely, the V can't go anywhere else. So his first thing is he's going to block the V because, as a reminder, if you can't make a play, you're basically just passing your turn, and so Nigel will just be able to finish the game optimizing his remaining letters without even considering ramifications from his opponent. So he first blocks Vow, and then he makes kind of a curious looking play of just ED for 3 points. If he can maximize what he has left without worrying about what his opponent can do, what's the point of this? Well, there's a weird three-letter Scrabble word, EDH, and what he's actually doing is giving himself the ability to play athleisure with some of his remaining tiles. And so like athleisure wear. Really, really pretty find and right, it hits the triple word score in both directions, so it's a 60-point play. And then he just uses his last tile, the O, just in its maximal spot. So this is the optimal endgame sequence. Quite pretty and hard for most humans to find. Nigel found it very quickly. And an engine can also solve this very quickly. All it does is we're going to basically be making the tree of all possible moves and using tree search algorithms to find the maximum. That's how a computer would solve it. So let's increase the complexity slightly. Now, instead of just having one tile and we know what our opponent has, let's suppose there are 8 tiles unseen to us, where our opponent will have seven, and then there's one in the tile bag. So we now need to potentially go through 8 unique permutations, although I guess in this case there are two ends, so 7 unique permutations of possible um, considerations to have. So came from a game of myself, and I'm down 57 points, which seems like a lot. But the nice thing is, I have regimen making two valid two-letter words as well for 70 points as an option. So even though I'm down 57, I could take the lead here by 13. The problem I noticed though is that so Scrabble, there's some weird Q without U words, And this would actually allow a really high scoring counterplay if my opponent has the Q, the A, and the T. Specifically, COTS, making all these valid words, would score over 70 points as well, just because the Q's a 10-point tile, a triple word score in both directions would quickly make the game untenable for me. So if my opponent has those three tiles, I'm going to lose no matter what. So I'm resorted in analyzing this play to consider what if the final tile in the bag is one of the Q, the A, or the T. Right, there's seven of these eight tiles are on my opponent's rack. The eighth I will draw after I play Regiment. So when doing this, I noticed that the Q, if I draw it, wouldn't win the game, but the A and the T, if I draw one of those two, I would win the game still. So it gives me a 2 in 8 chance, which is better than zero. So definitely I'd still consider among my candidate playset, but maybe I could generate something that has a higher probability of winning. And the move I came up with looks a lot worse at the surface, but actually was what I decided on. So the play I made was on, just for 3 points. And does anyone maybe see the logic behind this? With keeping in mind that last turn, if I kept the N, I would be able to play Regimen. Any ideas? Let's see. So So let's actually see what happens and maybe what could happen, and this could maybe explain the logic. So I see one comment. Yeah, so open up a second spot, basically. So the idea is that if I redraw the N, not only will I have Regimen at the top of the board, but I can make one and Regimen on the other side of the board, right, in a completely different quadrant, such that my opponent can't block it. And since the game ends when the tile bag's empty and one person finishes their tiles, the timing of this works out a bit better where I will end the game. If I play Regimen, my opponent can't have some high point counterplay as a result thereafter. So I can kind of have my pick of the litter. So, and if we actually run this out the scenario where I draw the N, uh, it would look like this, where my opponent would just make their highest point play, and then I just end the game with Regimen in the other spot. So this means since there are two ends in the bag, this would give me a 2 in 8 chance of winning. But for the other tiles, I went through the permutations and that wouldn't work. So naively, this looks like just as good of a play. But the other thing I noticed was my opponent on the previous turn played Drool, and it would have actually been strictly better if one of their two other remaining tiles was an N for them to make a different play in the same spot, Rondo. And so with that information, you can actually deduce just using like conditional probability or Bayes formula that we actually have a 2 in 6 chance of winning with this play, given that information of what the opponent did in the previous move. So we can already see that adding some uncertainty to a situation quickly makes this a more complex problem to solve. I was able to solve it within minutes, but a computer now goes from being able to solve this within seconds to minutes, both because of the task of now iterating through 8 unique permutations, but also just the inference aspect of what my opponent could have been keeping the previous turn. So the third motivating example, I'm not going to go as in depth analyzing lines, but this now gets even more complex where not only is there one tile unseen to or in the tile bag, but now there's four. Seven will be on our opponent's rack, and four will be in the bag. And this time there are 11 unique tiles, so we truly need to go through 11 unique permutations rather than 7 out of 8 in the last position. So here I'm winning by 17 points, and I consider two candidate plays. One's the high scoring move, where it will lose, I notice, if I draw the Q, and in a similar way to that first position where the opponent was hamstrung with the V, if Nigel blocks the one spot it could play, right now QI over here is the only place on the board where the Q can go. So if I don't draw other tiles that allow me to play off the Q, I could have a similar fate. And that's what happened in this game. I lost by 1 point. But from computer analysis, it wins 84% of the time if we actually go through all unique four tile permutation sets of what could be in the bag. The other play I considered kind of remedies that downfall of that previous idea where GI is a word, and since I'd be keeping an I playing gyms here, I'd be able to play QI and GI here, or have QI at the bottom of the board. So it kind of gives me guarantees if I draw the Q. But I noticed this scores so much fewer points in a lot of end games, I would be exposing myself to new risks. And so I decided that even though it alleviates our concern if we draw the Q, the other risks are large enough. And so the computer actually confirmed that my between these two choices, my decision was correct. It wins 67% of the time. The problem is the time it took for my computer to analyze just these two decisions was each a week. And so this isn't actually even considering all possible moves in the position. This is just the two candidates I generated. There could be a much better move that I didn't consider at all. And right, this is kind of the outer limits of just a deterministic tree solve, where once we start ha needing to consider all these permutations and right, four choose three or whatever, I guess, in this position. Or I guess, well, yeah, we need to do 11 choose three also in that calculation. These are going to quickly explode as we have more and more uh, unseen tiles in the pool. So what makes Scrabble a really difficult game to analyze in a different way than games like chess or Go? First, we can see there's kind of this enormous discrete action space. So if we ignore the placement of words even, it includes over 150,000 valid words, and technically phony words can be played too. You could say, well, in a specific position, a lot of those words aren't actually accessible. Still, the size of the action space for a given turn varies much more than that of other games. There are other, I think, subtler things that are actually also, though, really important to remember, especially from like a statistical learning or a machine learning perspective. One really big one is there's kind of non-recurrence or just very weak generalization across games due to the random permutation of the 100 tiles. And so what do I mean by that? Well, if you go back to some of the original chess engines, like IBM's Deep Blue, for instance, it started with a known database of solved endgames in chess. And if you know an endgame result, like a decisive result of a win or a loss or a draw, I guess in chess, you can actually extrapolate that to a bunch of other positions, right? You can add a superfluous piece to the board. You could go back a turn. You could maybe like mirror the position or something. And a lot of things if you know one position, it unlocks the ability to know something about a lot of other positions that can occur frequently in chess if you actually fully play out a game instead of resign at some point. In Scrabble, because there's these random permutations, with basically probability one, any game you see won't have that kind of direct ability to generalize to any other game in the future that actually will be realized. So so in that sense, learning something about one game has very little direct applicability compared to these other games that have been solved by or have been not necessarily truly solved, but have created very strong engines by Google and such. Another issue is that there's a severe signal to noise problem in move evaluation, in the sense that if you actually look at the results of a game, outcome variance induced by just the random permutation of tiles can dominate strategic effects to the point where one could always make the best move and still lose while their opponent isn't making the best move. Case in point, Nigel Richards, who's the best player in the world, wins around 75% of the time. It's not because for that other 25% his opponent's outplaying him, it's that his opponent just drew better tiles most of the time. So uh, a lot of games where, especially like where reinforcement learning is used, where you reward one end if you have two engines playing against each other, you reward one side if they win. There's this random element that kind of obscures that signal. And finally, there isn't really a known low-dimensional sufficient description of move quality as well to sort of summarize the quality of the move. So if we actually consider the architecture of these sort of incredible deep learning methods that Google DeepMind's created, like AlphaGo for Go or AlphaZero for chess, it probably will look different than if we were able to have a deep learning engine for Scrabble. Specifically, in those games, we kind of they're entirely spatial. You just need to consider what's actually present on the board. Whereas in Scrabble, you also need to consider the contents of the bag. So we're going to start out with a much wider set of covariates. But beyond that, because those other games are much more generalizable game to game, you probably are able to factor them a lot more smoothly or factorize them a lot more smoothly. Whereas in Scrabble, so like the architecture of those games have some sort of initial convolution layer in their convolutional neural network. And then thereafter, there might be a lot of layers, right? There could be a high depth, but usually those are going to be pretty narrow because it kind of all can factorize eventually at some point with enough interactions between the neurons. Whereas in Scrabble, if we don't think there's that generalizability, each layer will probably have to be a lot wider. We can't kind of put many games into buckets in the same way. And in kind of theoretical neural net research, it's often the key bottleneck in terms of a neural network being able to converge or be a good estimator of a problem is the maximal width of any layer of a neural net. So we could be inclined to think that uh, even what we think a good conceptual model should be for a deep learning model for Scrabble might actually have problems from an estimation perspective. So hopefully that gives some insight into what makes Scrabble a difficult game to analyze at a high level. Does anyone have any questions before I kind of go into the specifics of what's actually been implemented?
I did have one, but I
Yeah.
don't know how relevant it is in this point in the talk. And I kind of asked this coming from like a personal space playing Scrabble. How much of an advantage is you being the first person to play a word? Particularly like I've been in a couple of games where like I can kind of hit out all seven of my letters in the first play, straight from the from that initial and if I kind of maximize the like double word score and then the triple letter score on like either end of the side of the like the middle section of the board, I feel like that has been my strategy, but I don't actually know how effective it is.
Yeah, so I think it's I forget the exact number, but it's like player going first at an ex in expert games
Hmm.
wins around 54, 55% of the time. So there is an advantage, but it's not a lost cause if you are going
Yes.
second.
No, and I can agree with this because I played two games simultaneously with the same person to try and like vet for this issue of like, yeah, like he'll start first and then I'll start one. And because they're going at the same time, it's like, well, we're trying to figure out like who's actually the better
Yeah.
player.
Yeah, and the one other comment I'll say on this is actually in like using in testing out different engine architectures, often technique that's used today is kind of play out the same game but flip which side goes first and which side goes second, essentially, right? So right, like choose a permutation of the 100 tiles and just kind of switch which player kind of starts with which stuff. So to actually directly compare engines. So it is actually kind of a neat experiment from a testing perspective, if that
Yeah.
makes sense too.
Okay, very
Um,
cool. I'll look into
yeah.
this. Thank you.
And I see Eric has a question as well.
Yeah, Morris, so I hear you about like alluding to the differences between chess and Go, and like it's much more multimodal, Scrabble is, and some of the difficulties there. But on the other hand, unlike chess and Go, you have an extremely high signal turn to turn because of the point scoring, which chess and Go don't, right? And even though, say, points on turn one is only very weakly correlated to points on turn, whatever, 30 or wherever, however long Scrabble takes, surely that gives an edge in some dimension, right?
Yeah, that's a good point. So to be clear, in terms right, like if the score differential is too large at some point, basically no matter what one player plays, it won't change their win probability. So that is very fair. Um, But but the thing I'll say is that we'll have good kind of like good surrogates for what the true move quality is, but it's not going to be nearly as precise, right? Yeah, heuristically, we'd think just scoring a lot and maybe keeping good letters that are conducive to scoring the next turn should be pretty good, and that's kind of how a lot of engines have been created up to this point. I'll kind of go through that in a few slides. Um, but yeah, these aren't precisely relating to win probability, direct solves of win probabilities, if that makes sense. So there's sort of that battle.
Makes sense. And I wonder if it's also related, therefore, to like exploration, exploitation, kind of classic trade-off there, which is you can for sure maximize short-term points, but you could then narrow your ability in future turns. So
Yeah, exactly. And the issue really is basically doing that exploration, right, like actually fully figuring out what the consequences of a move could be a few turns out just explodes so much quicker than so many other games. So really good questions. I'm gonna start moving on because I think the questions being asked are kind of touching on what's already been implemented. So hopefully it also sort of clarifies other questions people have. So for the past, I'm actually going to start with not actually talking directly about an engine, but the inspiration behind a lot of engine analysis. And this comes from Ron Tiegert, an expert player who was the US national champion in the 80s. And he started with this opening position with the letters AAADERW. And so most experts at the time would have made one of two moves, either Weird, which is the highest scoring play for 26 points, or they would sacrifice 4 points and play Award, with the idea being that keeping two A's after Weird versus AE limits your options comparatively. If you keep duplicate tiles, just the number of possible moves you can make the next turn will shrink. So presumably you could be able to recoup more than 4 points by sacrificing 4 points this turn. Ron went a step further and actually sacrificed many more points. He played Awa for only 12 points, so 14 points sacrificed from the most, 10 points sacrificed from the second most. And the idea is that ADER are especially synergistic at as a set of four tiles that maybe he increases his score even more than just the 4 point recoup potentially between the first and second idea. And he showed this to a bunch of experts. They disagreed. So depending on your outlook in life, he was either very curious or very stubborn. And he did the following. So he actually just sampled from a tile bag random permutations of upcoming tiles, uh, assigned right the first seven to his opponent, then the next however many to what he replenishes after his play, and then continues on. And he did this for three moves, so his opponent's next turn, then his response, and then his opponent's response after that, and just calculated what the net differential was for any permutation he drew. So in this example of the sample tiled order, Awa does net the highest point differential to the point where the point sacrifice is totally worth it. And he did this 50 times. And he found that his play actually was getting the best net differential. And if we actually use this, so he's basically doing a Monte Carlo simulation by hand. And so if we do a Monte Carlo simulation now on a computer, uh, it does take longer than 50 iterations to actually find statistically significant, yes, this is a better play than the other two, but we do find the same result today. And it actually is estimated to win 3.5% of the time more often. So this is sort of when we kind of can't use this kind of perfect tree solving or tree search algorithms when we're in more complicated positions, we use Monte Carlo approximation basically to try to analyze how good a play is. And so this was integrated into kind of the first computer engine Scrabble. Harvard PhD candidate Brian Shepard in the computer science department built a Scrabble engine for his thesis. He called it Maven. It was first developed in 1983. A lot of the focus, since he was a computer science guy, was focused on actually like fast move generation and being able to build data structures that actually find the complete set of possible moves. And so, but he also did some like statistical learning aspects as well. He built an endgame solver using tree structures and known optimization algorithms. And he talked with experts, including Ron Tiegert, and that inspired him to build a Monte Carlo simulation feature. Now, the other thing I should mention is that's a key detail is Ron, being an expert player, was able to, when drawing seven random tiles, choose what a best play should look like. How does a computer do that? Well, Brian Shepard, he basically estimated the expected point value of every subset of 1 to 7 tiles from computer self-play. And then he had Maven rank moves pre-simulation by sum of the immediate score plus this estimated expectation of future score from the remaining tiles. So Awa would only have been 12 points, but presumably this expectation term could be larger than Waird's, to the point where it might rank higher in equity as a response. So he wrote a paper on his findings with Maven, and he also experimented with other ideas, like actually considering if you want to make open plays, closed plays, basically like board dynamics, and considering the consequence of your play for what that unlocks for your opponent. But he found that including parametric estimates for this actually degrade performance, which was against expert advice. So he threw some shade at experts in the paper. He said experts often do not know which move is best, let alone why it is best. We resolve to test every theory. In reality, he didn't really systematically validate his hypotheses, and most likely these negative results reflected modeling challenges of what sort of models he was considering and what was available at the time rather than completely baseless guidance. Um, and the other kind of shade he threw was the biggest challenge in the world of Scrabble AI has met, because no one seriously disputes that Maven is better than a human. Um, really, because Maven has the ability to find every possible play, that's a significant edge, especially in those days where players didn't have computerized self-study. So players could miss candidate moves, so they'd be worse play finders, but they might be better decision makers, conditional on seeing the full set of plays. So it's not true today. Nigel Richards, people think, is better than the current state-of-the-art Scrabble engines. Um, but to be fair to Brian, he did kind of give some humbleness to Maven. He said the real challenge is whether Maven can be improved upon. There are several avenues to explore, but the total improvement will only be a few points per game. So in the next 10 years, there were a few other engines that came out, and I wrote kind of a pretty comprehensive set of updates they made, but the key thing to take away from this is that these engines are still built around the same sort of architecture idea that Brian created, where there's kind of really fast computer science data structures that allow move finding. You can have exact tree solves in endgames and in positions that we aren't able to kind of fully expand the tree. We use Monte Carlo iteration, and it's kind of based on a heuristic, this equity idea of points plus expected value of what tiles you keep. And you can improve upon right, that estimator for the value of the tiles you keep, and you can improve the computer science efficiency, but we're not actually changing the underlying engine structure. We're not having the computer do anything different from trying to gain insight about a position. So, but to be clear, these definitely improved the game a lot. But it's all under the same sort of architectural framework. So where are we on the present? Well, there are kind of two concurrent efforts to improve Scrabble engines. So I think I saw Cesar here. He's the main developer behind Macondo. And again, he's kind of built out a lot of great features that improve this sort of Brian Shepherd architecture. And there are some other things, like he's developing a Bayesian inference method for opponent tile leaves. So, like in that example position where I was able to determine one of the candidate plays is actually a 2 in 6 chance of winning instead of 2 in 8. That sort of stuff is available. Magpie was at first just a complete clone of Macondo, but they now have added a few other features. One interesting one is they basically use stochastic multi-arm bandit literature to kind of efficiently consider all candidate plays in a Monte Carlo simulation and slowly dwindle them down until it reaches an optimal selection policy. But these are still based around this sort of idea of, in the Monte Carlo simulation, we're assuming some sort of heuristic for opponent responses. We're not actually like fully solving a game, and we're not like using artificial intelligence here, like Google DeepMind sort of does. So, but that doesn't mean we're not looking at more things. So, Cesar has also started to train and to be clear, like a lot of the advancements they're making in these sorts of things are very large. Now it's like orders of magnitude faster to actually process a Scrabble game than previous engines. So I don't mean to dismiss what's been developed here. It's really impressive from a kind of computer perspective, but now we're getting to the point where we might want to expand sort of statistical learning aspect. So, so Cesar has also started to look at kind of a neural network engine. And so what he's been doing is training an engine that just plays the top equity move against kind of another engine that actually uses a neural net. And the cool thing is, so his FastML bot is the neural network bot. This hasty bot's just assuming the top equity move. So, assuming the top equity move, that engine scores more points on average than his neural network engine, but it loses more often. So it seems so wins only 48% of the time, but scores 11 more points, this kind of static engine. So it seems like the neural net is able to pick up on some nuances of even if we can we're sacrificing points this turn, um, it is a more conservative play, but that's also true for our opponent. So it knows kind of when to sacrifice points and not be entirely greedy to some extent. The issue is that compared to just a Monte Carlo simulation engine with kind of using the heuristic as a response of top equity, um, that wins significantly more often than just almost 52% of the time. It's closer to 60% of the time against this kind of static equity engine. So while the neural net can improve upon a static equity, at least right now, it's not nearly as good as a Monte Carlo simulation-based engine, at least currently. But there's still flaws with the Monte Carlo simulation. So one really evocative position from this past summer in the same tournament that I showed that athleisure example earlier, uh, Nigel Richards' best player in the world, in one position he chose to exchange 5 tiles rather than playing a scoring move, and all the engines, no matter which one he chose, recommended playing a scoring move rather than exchanging. And so in this position, he's up by 53 points, but the remaining tiles are conducive enough to his opponent playing off all of their tiles potentially next turn. So that 53-point lead could evaporate. Oh, I see actually some comments. Um, okay. So what's the reason why Nigel diverted from the engine? Well, the engine concluded that even if the opponent, so Ali was most of the engine's top recommendations. So even if Nigel plays Ali and the opponent is able to play off all 7 of their tiles with something like Studier, that doesn't actually cause too many problems for Nigel. You just continue the game and Nigel will still win, not by a lot of points, but Nigel would still win. So the engine concludes, you're fine here, just take the points and you should still outrun your opponent. The issue is that assuming the top equity move of Studier as the opponent's response, right? And top equity is just the sum of points plus the expectation of the remaining letters. So if Studier scores 70 points, you're not keeping any other letters, so its equity value will be 70. Um, that actually isn't the best play if you run a Monte Carlo simulation from that position. The better idea is to actually kind of time it out better and wait patiently to try to guarantee playing off all 7 of your tiles at the very end of the game. So given that there are 14 unseen, that means there are 7 in the bag and 7 on the opponent's rack. If they instead play off 2 tiles and create a second spot on the board and they're holding the last S, now they can get a 7-letter word here or in another part of the board, right? Either alongside Ali or pluralizing woe. So basically, if they time it out better, uh, they're actually in a much better position. So they can sacrifice immediately, but if we actually play out an example where they draw AL, they'll win the game here. Whereas if they play Studier first and draw AL, they lose. So is the computer wrong? Well, the thing to remember is this Monte Carlo simulation engine, even though it really outperforms a neural net as implemented currently, it implicitly assumes that a human opponent's response is well approximated by the top equity play. So in some ways, we can think of this as basically like a low fidelity simulation approximation of actual human play. We saw in that specific example, it's not going to be the case in a lot of like pre-endgame or endgame positions to just make the greedy play. And it's less obvious in mid and early game positions, but I'd venture to say that most top experts divert from the top equity play at least 3 times a game. So, so it seems like this is kind of a nice heuristic approximation to some extent, but we're not actually directly mimicking how optimal opponents would respond in these Monte Carlo simulations. Um, So the other thing I'll just say is extensive post-hoc analysis from top experts confirm that Nigel's choice has a strong case for being the best play in the position. There's a really good YouTube video about it. I think it now has over 400,000 views. I think the creator I saw in this presentation at some point. Definitely check it out. I'm interviewed in it. Um, and so um, but the question is, can we improve Monte Carlo simulation? So, really recent development in the past few weeks is that the developers behind one of the engines has begun testing out a nested simulator, where you're not just for any candidate play, assuming the top equity play, you try to optimize per ply or like future turn of the simulation as well for every iteration. And so, at least from initial testing, this significantly performs this kind of naive, low fidelity Monte Carlo simulation engine, but it's quite expensive to run. And so, tests were performed on a really shrunken candidate playset. Right, so kind of the naive low fidelity Monte Carlo simulator, you can consider all possible moves in a position. This, if you're optimizing for each turn in any iteration of the simulation, uh, you can only reduce it to a very small possible set of candidate moves. So that's kind of where engines are up to now. I'll quickly go through some things that I hope we'll get to do in the future. So the first is moving from thinking about this as a discrete problem to a continuous problem, and changing the problem from like this kind of discrete bandit policy identification perspective to some sort of locally adaptive procedure where we optimize within some continuous space. So, right, the standard Monte Carlo simulation is discretely evaluating only some top P set of plays. In the cheap low fidelity version, you can consider all possible plays in the position. When you start to move to this nested sim, you have to cut off the number of plays you consider significantly. But instead, what if we embed all legal plays into some high dimensional continuous feature space where like any axis will represent a specific feature about a play, right? The number of points it scores, for instance, an estimate of the kind of tile value of the letters kept, some sort of board dynamic sort of features. And then the goal can then be to just identify an optimum in that manifold that you create in that high dimensional space, rather than kind of discretely considering each play without sharing information between what you've learned about any individual play you've analyzed. So just a potential procedure, you just initialize some p set of candidate plays covering a broad region of the manifold, and then you run a very small number of Monte Carlo simulations per play to estimate win percentages. And then you fit some flexible function, such as a Gaussian process, to the full manifold based on the small set of points you estimate win probabilities for. And right, so that's going to be some sort of estimate for win probabilities for all plays, possibly. And you retain some top portion of the P plays. And for the others, you can use like gradient descent based on your estimated function to actually improve what the next candidate play you'd consider could be. So, and so we just iterate that until we have some sort of convergence, like the top K play stabilizes. But something like this allows for a more holistic way to consider all plays still in a relatively efficient, only considering a small subset of possible plays. Um, Now, the issue with this sort of procedure, if we apply that nested simulation idea and try to have a high fidelity simulator, is if we apply this adaptive search at every ply or every future turn in an iteration of a Monte Carlo rollout, it's going to be very computationally expensive still. So if we consider the number of candidate plays as P, capital P, and the number of plies are basically future turns in any iteration of a simulation as lowercase p, and the number of permutations in our simulation is I perm. The standard kind of low fidelity Monte Carlo simulator is going to be, in terms of computation cost, a function of the product between those three things. Whereas here, if we actually start to have shallow simulation on any set of candidate plays, and then have some sort of adaption amount, and then that's only for one iteration of a Monte Carlo simulation. We'd want to consider other random permutations of what tiles remain in the bag. We can quickly see this is going to be a much more complicated problem from a compute perspective. So to the point where we need this like I prime perm to be much less than I perm. So, for this to be viable, we could maybe take inspiration behind existing Monte Carlo literature. And the idea here is that even though we'll analyze a lot fewer random permutations of tiles, if we have this kind of high fidelity simulator that's pretty comprehensive about scanning the full space, each adaptive iteration will extract substantially more signal per permutation. So the idea here is maybe we can exploit antithetic variates. So for those not familiar with this idea, basically in Monte Carlo simulation, you can shrink the variance if you basically if you for any random draw you do, you also draw a negatively correlated version of that specific draw, with the idea being that variance is the sum of the variance of two unique random variables is the sum of their individual variances plus their covariance. If their covariance is negative, then that will shrink the variance overall. So we might want to actually try to create some sort of permutation similarity score. And I just kind of float here a potential way to go about that, where you basically create a bunch of game positions and then randomly draw a set of possible permutations upcoming and just calculate the win percentage for those. And then you do some sort of matrix, latent matrix estimation process for just the random set of racks. But you can use fancier models like a variation autoencoder. The big idea here is that we're not going for cheaper simulations, but far more informative permutations, and to be able to use this high fidelity simulator in a really productive way. And so then and only then, I think once we kind of have a really high fidelity simulator, then we can maybe use that as a training signal for deep learning models to use them most effectively. Right, once we have continuous play embeddings, that provides a very rich set of covariates to feed into a model. And also these high fidelity simulations give us much better signal than just using a heuristic. So like Eric's question before, well, don't we kind of have this check-in point of every turn of the score? Well, now we're not just relying on like a heuristic for that. We can maybe have much closer to true best play mid-game signals. So two ways in which we can carry this out. One is we could actually try to find the optimum using the high fidelity simulator and just tell the neural net these are good plays for specific turns. But what we could even do instead that's even simpler is we could just, in a bunch of positions, just analyze a few plays randomly chosen and keep track of the win probability estimates for both the high fidelity simulation and the low fidelity simulation, and have a model try to actually learn the error term of basically the low fidelity model. So, but basically the key shift is, rather than relying on self-play reinforcement learning from scratch, we want to train models to imitate a very high fidelity simulator, since those seem to be quite strong. And once distilled, reinforcement learning can maybe then be applied against kind of this strong initial fast surrogate. So I realize I've gone a bit long, but to wrap up, I'm just going to leave you guys with this quote by Garry Kasparov, one of the best chess players of all time. Chess has been used as a Rosetta Stone of both human and machine cognition for over a century. AlphaZero renews the remarkable connection between an ancient board game and cutting-edge science by doing something extraordinary. So in general, why like AI companies often care about board games is they're considered kind learning environments. We have things like structured rules and clear feedback in the form of wins and losses. But we see once we introduce this random component, it isn't nearly as kind of a learning environment. Scrabble illustrates kind of the limits of kind learning under randomness. The random tile draws bias reward signals in key game states. And also this randomization reduces the number of what I say near isomorphic positions, or basically generalizability across unique games. So the two questions I'll leave you with, one is very game specific. Can we use rich or high fidelity Monte Carlo methods to improve mid-game signal beyond kind of a standard surrogate reward setup in other partially kind or even unkind environments. And more broadly, when randomness is structured and enumerable for not just games, but problems in general, should we instead try to have some sort of Monte Carlo procedure within the pipeline for training deep learning models? So and if the answer is yes to either of those, Scrabble may be a toy example, but the structure of its randomness may make it in some ways a better Rosetta Stone for many problems we care about. So thanks so much.
Thank you very much, Morris. That was fantastic. I'll stop recording.